Hello, can you hear me?
Yes, sir.
Okay. So in the previous class, we were talking about computer arithmetic. So I would like to finish multiplication today. So we started discussing one algorithm for multiplication. You remember that the school level algorithm, right? And we presented an example that to show that if it is a negative number, then the result may be invalid. So in general, what we do that we consider unsigned multiplication and then later on adjust the sign. And subsequently, we will study Booth's algorithm, then you will see that how this negative number can be handled. Okay, so unsigned multiplication is sort of, you have zeros and ones, so two strings, A's and B's. And then the idea is very simple, so if A's and B's are all zeros and one, so all you need to do is to look at this multiplier and consider these product terms, right? Okay. So basically you are looking into the most significant, least significant bit of the multiplier. And then if it is 0, then all these elements will be 0. If it is 1, then the multiplicand will be copied. And in order to determine that, from hardware perspective, all you need to do is to bit by bit AND operation. So the if we consider the implementation of the whole thing in hardware, as we see that it's some kind of, it's sort of straightforward, isn't it, sir? Because all you need is an array of AND gates to compute this partial product and then keep on adding them together. And we have already seen that if we have multiple rows, how to add them efficiently. One possibility is to use Karatsuba and so on. So that we discussed last time, right? And also we observed that if we multiply an n-bit number by a m-bit number, then the result would be you should keep an option for n plus m bit, because the result would be sum of the two digits of the multiplier and the multiplicand. Okay. So as far as the hardware implementation is concerned, all we need is an array of AND gates and then an addition process, right? And that's what you have seen in the previous class, that so if you have these partial products, and then in order to generate this partial product, I use a series of an array of AND gates with appropriate inputs. These bits are from the multiplicand, also from the multiplier. So you have the series of AND gates which creates this product terms. And then you collect all these bits together using an array of full adder blocks. To add them together, you get the result, right? So this is just a straightforward implementation of the conventional multiplication process that we have learned in our school. And obviously, because of this architecture, as you can see that we are concerned about delay, and here, because of this architecture, as you can see, the propagation delay is still linear, right? It's 2n, because the signal has to flow horizontally as well as vertically. We have little bit option for changing this architecture to a carry-save addition process, where you can break this horizontal flow of signals and instead you can transform them into diagonal signals, thereby improving, reducing the delay a little bit. Okay, and so as we remember that when you add multiple numbers, you have the option for, and this is the typical way of arranging the adders, replicatory adder in a two-dimensional array. Instead of doing this, you can break this connection and take this and consider this vertical connection, this diagonal connection, so that the signal flows downwards. And in that process, we said we reduce the delay to some extent. And this is the principle of carry save addition for adding multiple numbers. And the same thing can be used here, right? So in this diagram, what you show that this is an example of a 4-bit array multiplier using the carry save adder principle. So here, if you look at it carefully, is the same architecture, the same circuit. So these are the arrays of AND gates which are producing this the partial product, and these AND gates are fed with the bits from the multiplier and the multiplicand. And then if you look into these full adder blocks, see this horizontal flow of signal that is broken now. So they are not operating as a ripple carry adder, right? Instead, the signal flows from in a diagonal direction like this. So all these carries are being not utilized in the next horizontal stage, but conceptually they are being saved and they are being used for subsequent in the subsequent stages of addition. Finally, everything is collected using a full adder's ripple carry block here, or this may be changed to a more improved version of addition. So you got the idea, right? How you can change this architecture by using carry save addition, correct? Well, and so what will be the cost of this this kind of architecture? You have 2 n-bit numbers. How many AND gates we need?
N square.
Yes, n square. So this cost is quadratic. So remember that later on we will pass on to a different algorithm, and in order to save this cost. Okay, n square AND gates you need, and computation time is also because although these AND gates are working in parallel, but otherwise this because you need to compute n square partial product anyway, right? And then you add them together by some mechanism. Well, so that is the overall story of the array-based multiplier. And I show you some, as we have seen that in case of carry save addition, we can use this kind of tree, and this is known as the Wallace tree, which means that, so these are the carry save addition blocks, and each block has 3 inputs and 2 outputs, right? So thereby, it's a 3/2 reduction at each step. So if we arrange them, this carry save adder blocks in the form of a tree, so this will have a depth of this kind of thing. This is a log 3/2 base, and how many inputs are there? That is the n. So using the same principle, you can also use here in the case of multiplier to save time, right? So now, so this is a diagram for 16-bit array multiplier using carry save addition. So one thing is, you may notice that it has a very regular structure. Signals are flowing diagonally, as you see. There is no horizontal flow of signal, and the partial products AND gates are not shown here. It is assumed that the AND gates they have been already, those partial product terms, they have been already produced by an array of AND gates, which are not shown here. And then those signals we assume that those signals are available at the inputs to this array logic. So here only the array of AND gates have been, the array of full adder blocks that has been shown. So it is conceptually straightforward if you just utilize this concept, but it's fairly expensive hardware. So these are called array-based multiplier or array multipliers. Okay, so in order to avoid this, if we want to, in computer architecture, we frequently talk about trading off the cost and speed and so on. And in MIPS, for example, in MIPS architecture, what we do usually that we emulate the multiplication process in hardware by performing repeated addition and shift. So what you do actually, if you have a multiplicand and multiplier, what you are going to do? See, if this bit is 1, and then you copy the multiplicand, right? And if this bit is 0, all bits are 0 here. And at every step, you are just shifting this partial product term one bit to the left and then finally keep on adding, right? So now suppose I'll supply you a basic adder block and some registers, which are already available in the MIPS architecture. And instead of providing you the array of AND gates, I would just ask you to keep on adding this in a repeated fashion and implement the shift by the typical shift operation in MIPS. So you can do that, right? If you are given a CPU and a register and a shift instruction, you can easily do that, right? Isn't so? So you don't need this array of AND gates and so on. So so this diagram actually reflects this, that how you can do this. First of all, let us assume that this multiplicand, that means this guy, is saved in a register, and the multiplier is saved in this another register, and the result would be saved in this register. So we assume that we have a 32-bit multiplicand and 32-bit multiplier as in MIPS. And let us see that how this architecture works. So what you do that if you look into this the multiplication process, what you check here, first of all, you check it the least significant bit, right? That means the rightmost bit of this multiplier. So what you do here, we keep the multiplier in this register, and you check the rightmost bit here. And depending on whether this bit is 0 or 1, if this bit is 0, nothing to be done. Only thing that this partial product term has to be shifted a little bit. See? And that's why there is a shift left mechanism here. So this multiplicand can be shifted towards the left at each step, regardless of this fact that whether the rightmost bit of the multiplier is 0 or 1. And as soon as you are done, so then you shift the multiplier towards the right so that you can now examine the next bit here. Okay. And there is a controller here which checks about whether the corresponding bit is 0 or 1. And depending on that, it takes appropriate action. And when 32 bits are exhausted, it gives the stop signal. So this is the ALU which is performing this repeated addition at each step. So the multiplier is available here, and the sum of the partial product that is available here. So keep on adding this, and finally, when the controller says that well 32 bits are exhausted, the result is available here. So please look into this diagram a little bit carefully and see whether you understand the process. So first of all, okay, let me ask you, why do you need this? Why this multiplicand is 64-bit wide? Because we have assumed that both multiplicand and multiplier, they are 32-bit. So why this is 64-bit wide? Product term has to be, the result has to be 64-bit, right? So this is okay, the final product will be saved here, that's fine. But why for multiplicand we have kept 64-bit register?
We are shifting it 32 times, so we need to take care of that 32 times.
You're right. And this 64-bit ALU, because I mean, if you consider this staircase, imagine that you have padded this blank entries with 0. Similarly, you have padded the blank entries with 0 on the left side, right? So therefore, that's why a 64-bit ALU is used here. So here, as you can see that this architecture uses a 32-bit register for multiplier, a 64-bit register for multiplicand, a 64-bit register to save the final result, and a 64-bit ALU. And this data flow is obvious, right? So you check here the rightmost bit. If it is 0 or 1, you take appropriate action. Okay. And keep on doing this 32 times, and finally the product would be available here. So since in MIPS architecture the ALU is available, the registers are also available, and the shift operation is also available, you know, we can do away with this and array, right? This we don't need this and array to create the partial product. But as you see that so this is essentially sequential process. So you have to wait for 32 cycles anyway, right? In order to complete this product. Okay, so let us look into this in a little bit more detail. So as we have discussed, that multiplicand register is kept 64-bit wide because it is shifted 32 times towards the left. And we have used a 64-bit ALU, that because of the fact if you pad zeros with, blanks with zeros, then and the final result is of 64-bit. That's why we have used 64-bit ALU for simplicity. And product register must also be 64-bit wide. Okay, the content of the multiplier register is shifted 32 times to the right, and each bit, the rightmost bit, is tested successively, which is checked by the controller whether it is 0 or 1, and appropriate actions are taken, right? Okay, so let us look into this same example, the same architecture, and this operations is now given in terms of this flowchart. So this is self-evident. You know, you start here. This says this. You check the 0th bit of the multiplier. That means the least significant bit, rightmost bit. And if it is 0, and then all you need to is to shift the multiplicand register 1 bit to the left, and nothing is to be done. And if it is 0, if it is 1, so then you have to add the multiplicand to the product, right? Because this gives it gives the contribution to the product term, and then shift the multiplication register to 1 bit and keep on adding this. Okay, so add the multiplicand to the product, place the result in product register, and shift multiplicand register left by 1 bit and to process the next step, and so on. And at the same time, you shift the multiplier register to the right 1 bit so that the next bit can be examined here. All right. And whenever the 32 repetitions are completed, you exit and they're done, right? So now we'll see that since you are doing 32-bit arithmetic, can you reduce the size of these two registers, you know, this multiplicand register, and can you reduce the size of the ALU? We need to keep product register 64-bit, that's okay, but can you still reduce the hardware for multiplicand and the ALU? And in fact, we can indeed do that. And in the next diagram, this is explained. Okay, so this is a little bit modified or optimized version of the multiplier. And here, as you can see, so it has this design is a little tricky. You know, this multiplier register is now gone. So what it does, so we use a 32-bit ALU as well as a 32-bit register to save the multiplicand, and this product register is 64-bit, and initially to start with this rightmost 32 bits that is being used for storing the multiplicand, and initially the leftmost 32 bits that are set to 0. You know. Okay, so and this is shifted right, and so the controller checks the rightmost bit of the multiplier, and whenever it is done, the multiplier is multiplier bits are shifted out of this product register, so that this leftmost side, you know, you have more blank places here, and you need a 32-bit ALU instead of 64-bit ALU, and the multiplicand is 32-bit, and you can do this, you know. So I will show you an example that how this can be performed. So this is an optimized version where you reduce the cost of the hardware. You don't need the multiplier register, first of all. And secondly, you don't need a 64-bit register for storing multiplicand, and you don't need a 64-bit ALU. All you need is 64-bit register to save the product term as well as to save the multiplier initially. And as the multiplier bits are being shifted out, this product term is growing gradually, and finally the product term will occupy the entire 64 bit. All right. So let me give an example, and that will be it will be easy to understand what is happening here. Okay. So the multiplier 32 bits is saved here initially, and you keep on shifting it with each clock signal. Here is the algorithm here. So let us not just go through it carefully, and I am just showing an example that how it does. Okay. So here is an example that we have a multiplicand which is 2 unsigned multiplication, and we have a multiplier which is 6. So the multiplicand is this is a 4-bit example. So multiplicand is saved in a 4-bit register, and the product term will be saved in a 8-bit register, and the rightmost 4-bit of the product term of the product register is initially loaded with the multiplier. So you need only 2 registers, only one register for to save the multiplicand and another register to save the product term as well as the multiplier. Okay. So initially you have seen this, the controller examines the rightmost bit of the product term, which is 0 here. So there is no operation, right? Only thing you need to shift the multiplicand. So, okay, so this is loaded here first of all, and since this is 0, we don't take any action, just to shift the product term to the right 1 bit. So that means if you shift it, it is logical shift. So that means, see this 0, the rightmost 0 is out, and you feel the leftmost 0 here, so it's a logical shift. Now here you notice that, so initially there are 4 bits in the multiplier, now 3 bits are left. Okay, so the multiplier, this shifting of multiplier is making room for the product term. And then if the rightmost bit is checked again, this is 1. So we need to add the multiplicand with the product term. Okay, and so that's what we're doing. What is the multiplicand here? 0010. So that is being added with this part, to the left part here. Okay, so this becomes 0010 now, and you shift this right product. Keep on shifting this in. So iterate this, and this is being implemented with the hardware which was shown earlier. And finally, when this process is over, that means after 4 cycles, this is the iteration. You get the result is obtained in the product register, and which is, you can verify this is indeed true. This is plus 12. Okay. Any question here? This multiplication process simply emulates the repeated addition and shift. Nothing but the just emulation of the school level arithmetic. So we don't need the AND array to create the product term. All we need is a CPU and few registers and shift and addition operation. So if you already have a CPU, then you can use this kind of algorithm to implement multiplication. Well, sign multiplication is that can be adjusted later on, because if you have 2 operands A and B, then the sign of the product is nothing but the exclusive OR between the sign of A and sign of B. So what you do that in the algorithms which you have discussed so far, you just assume that the multiplier and multiplicand, they are positive values. You multiply them and then adjust the sign using this simple logic. All right. Okay, let me do one thing. I don't know why my machine has become slow today. Okay, so let us forget about hardware and multiplication and so forth. Let me ask you a fundamental question. So this is a fundamental question regarding multiplication. You are given two n-bit numbers. Here you are given two 4-bit numbers, for example, A0 to A3 and B0 to B3. And the fundamental question is, what is the, if you are adding two n-bit numbers, what is the complexity of multiplication? Just think of in terms of the algorithmic perspective. What is the complexity of multiplication? How many product terms do you have to produce? You said that there will be quadratic product terms, right? So think in terms of an algorithm, what would be the complexity of multiplying two n-bit integers? So that is the question. A's and B's are here, all zeros and one. These partial products you have to compute anyway, right? So what is the complexity of multiplying two n-bit integers from an algorithmic perspective? So this is a fundamental theoretical question. What do you think? Imagine that you have two n-bit integers and you are going to compute multiplication by whatever algorithm or by whatever mechanism for implementing the multiplication process. From algorithmic perspective, what is the complexity of the worst case complexity of multiplying two n-bit integers? So let us give you the abstract statement of the problem. Given two n-bit integers a and b, compute a cross b. Okay. So no matter what mechanism you follow or what implementation technique you adopt, you need this information, right? These partial products, which are quadratic in size. So this is the school method. Does it need, theta n square beta operation? And the related question is this multiplication algorithm optimal? So any thoughts in this direction or any comment? Can you do faster than quadratic operations? So this is a fundamental question, and this question was raised by, it was studied by mathematicians and centuries. It has challenged several mathematicians over the centuries. What is the optimal complexity for implementing multiplication of two n-bit integers? So you have heard of this mathematician Kolmogorov?
Yes, sir.
What was he famous for? There is a famous test in theory. Yes, probability theory. And in data science now, people use Kolmogorov's Smirnov test, right? It's a very famous test. It is still used it is widely used in machine learning and data sciences. Okay, so this problem was studied by mathematicians long ago. It's a fundamental algorithmic question, you know. And Kolmogorov was a legendary mathematician. And so he studied this problem, and in 1952, that's, you know, more than 60 years ago, or even more, right? So he conjectured that any multiplication algorithm would take omega n square beta operation. That is, it is asymptotically optimal because you need to compute this n square partial product terms. So he was convinced that yes, he conjectured, although he conjectured that it is omega n square. This is a lower bound, it's quadratic. And few years later, in 1960, he announced in a seminar that it is indeed optimal. It would take n squared time. Okay. Incidentally, there was a graduate student who was sitting in the audience. I mean, sorry, he was an undergrad student. His name was Karatsuba. That time he was only 23 years old. Okay. And Kolmogorov said that this multiplication is indeed omega n squared, so this is optimal. And during that time, no one had courage to challenge Kolmogorov. You know, he was a legendary mathematician. But this young gentleman, only 23 years old, after 1 week, he disproved the claim, showing that multiplication can be done in n to the power 1.585 times. Okay, this is amazing, isn't it, sir? So if you look into this multiplication process, which apparently it takes n square, I mean, you need quadratic product terms anyway, right? So how do you accelerate this? How do you do in less than quadratic time? So this is a beautiful result, you know, and one of the fundamental advancement in the area of the multiplication algorithm. And his algorithm was very simple, but but he uses a very simple trick in order to show that this can be implemented in n to the power 1.585. Well, here is this algorithm. This is Karatsuba famous algorithm for multiplying two n-bit integers a and b. Okay, let us assume that my laser pointer is not working today. So suppose these are n bits. This is a one number, and this is another number b, which also comprises n bits. So what we do, we let us say again divide and conquer technique. What we do that, have you studied Karatsuba algorithm in your algorithm course?
No, sir.
Okay. So this is a nice example of divide and conquer, you know, and is a very fundamental advancement in the area of multiplication algorithm. A very amazing result. So you partition this number, these bits into two parts, maybe n by 2 floor ceiling and 1 by 2 floor. Okay, and similarly you partition b into two parts. And let us call this. So if we look into this bit string, this represents a number, right? Just consider this half of this bit string. You know, this represents a binary number, right? And let this number be denoted as a1, and let this number be denoted as a0. And similarly, you partition b into two parts, and let the first part, the number represented by the first part is b1, and the number represented by the second part, the least significant part, is b0. Okay. So if I partition into this way, can I write this way? This number a, the original number a, is equal to 2 to the power n by 2 times a1 plus a0. And similarly, b is 2 to the power n by 2 times b1 plus b0. You agree? Do you agree with this? Because the weight of the leftmost half should be raised by 2 to the power n by 2, right?
Yes,
So,
sir.
So once you partition into A1 and A0 and B1 and B0, you can write the original number into this form, right? Where this both A1, A0 and B1, B0, they are n by 2 number. They are numbers of size n by 2 bits. Essentially, what we are doing is divide and conquer, but then there is a very nice trick later on. Just doing divide and conquer would not solve this problem. You need another trick to do this. And that's what Karatsuba did. Okay, so let us take the product of A and B. So you take this product of these two. So if we, and this becomes, as you can see, this becomes 2 to the power n A1 times B1. And then 2 to the power n by 2 A1 B0, also the cross product A0 B1, and finally plus A0 B0. Okay, this is simple algebra, nothing else. Okay, when you multiply the first two terms, it gives you 2 to the power n A1 B1, and the other terms are like this. Okay, so here notice that how many product terms you have to compute them. These are smaller product terms because the A1 B1 A0 B0 those are binary string of length n by 2, right? So how many different product terms do you need to compute? A1 B1 is one. This A1 B0 is another. Similarly, A0 B1 and A0 B0. So there are four smaller product terms you have to compute, right? So if you compute 4 product terms, then even if you do divide and conquer, the quadratic complexity would not have improved. So what Karatsuba did is a simple algebra here, a very tricky algebra here. So these are 4 terms that you need to compute. And if you compute these 4 product terms, then the complexity will not improve. What it did is the following, so look at this product term, this A0 B0 plus A0 B1, okay? So you can write it this way, right? So these two are algebraically equivalent. I mean, if you just expand this extra term would cancel out, and this will reduce to the original term. Okay. So the reason he did this expansion is the following. See, if you look into this term here, A1, B1, which is already here, so there is a common term here, right? So that means you can reuse this product term here again. And similarly, A0, B0 is computed here, and you can reuse it. You can reuse the value here, and this sum. So A1 and A0, this is the sum of two n by 2 numbers, and similarly, this is the sum of 2 n by 2 numbers. And this sum can be performed in linear time, right? And then we need to take a product of this. So how many distinct product terms we have to compute? Here is 1. Here is 2, and here is 3. And then we have 2 sum terms, right? So the total number of product terms after divide and conquer here, you need to compute is 3, not 4. And that does and this trick does makes the complexity, reduces the complexity from quadratic to that value. Okay. So therefore, what Karatsuba did is he replaced this term using this factorization form, using this factored form, and here you see that so there are 3 distinct product terms. One is here, this one is repeated here, 2 is here, because there is 1 product term here and 2 sum terms, and this is the 3rd product term which is repeated here. So what does it mean? It means that to multiply 2 n-bit integers A and B, you need to add 2 half n by 2. You need to add 2 n by 2 bit integers. You need 2 addition process of half of the size, and you need 3 multiplication process of half of the size recursively, right? And then you need some addition and subtraction and shift, because multiplication by 2 to the power n and multiplication by 2 to the power n by 2, nothing but shift operation, which can be done in linear time, right? Therefore, is the recurrence then? The time for multiplication n of n bit is less than or equal to t of n by 2. There are 3 multiplications, right? Because there are 3 distinct terms. So this is, forget about this ceiling and floor, because when n is not divisible by 2, that's why this correction comes. So this is t of n by 2, and again t of n by 2 plus t of 1 plus n by 2. Why there is 1 plus n by 2?
A1 plus A0 can overflow to one extra bit.
Yes, yes. If I do a plus a0, you get extra bit, right? One extra bit, and that's why this is 1 plus n plus n. Plus, what you need? You need this is theta n because you need addition process here, which can be done in linear time, and you need shift also. You need a subtraction also. Subtraction is equivalent to addition in binary arithmetic, right? And you need shifting also to implement this multiplication with by 2 to the power n, right? So anything which is multiplied by power of 2 is nothing but shifting left with so many bits, with n bits, right? So the recurrence goes this way. Tn is Tn by 2, Tn by 2. So there are 3 product terms like this. So it's 3 of Tn by 2 plus a linear term here for doing add, subtract, and shift. And if you solve this recurrence relation, that comes out to be of the order of n to the power log of 3. Okay, log 2 to the log 2 to the base 3, and that comes out to be n to the power 1.585. So now you see this beauty of Karatsuba's method. If you don't do this kind of factorization or this kind of trick here, then you would have 4 terms here, right? And if you have 4 terms, then this Tn would be less than or equal to 4 times T of n by 2, and in that case, this would have been log of 4, and log of 4 would give rise to n to the power n squared. So that means just by simply doing divide and conquer would not have solved this problem. The complexity has been reduced because of divide and conquer, and because of this trick of reducing the number of distinct product terms from 4 to 3. This is a wonderful algorithm. It was solved by an undergrad student only at the age of 23. And this proves the Kolmogorov's result or conjecture that multiplication cannot be done in less than n squared. In fact, it does. N to the power 1.585. This is a beautiful result and one of the fundamental results in the history of multiplication algorithms. Of course, hardware implementation of Karatsuba multiplication algorithm is little more involved, as you can see that you need to do this because this is a recursive algorithm sort of, Interestingly, after publication of Karatsuba's result this was published in 1962, the theorem by Karatsuba and Hoffman, one can multiply 2 n-bit integers of the order of n to the power 1.585 bit operations. Now, interestingly, this result is further improved later. And this was by Skonheis and Strassen. So they proved that it is possible to multiply 2 n-bit integers in log n, log n bit operation. So they used different concept from, they transformed the multiplication problem into a Fourier transform problem and then solved this accordingly. I think the name Strassen is familiar to you. Is this name familiar to you, Strassen?
So Strassen matrix multiplication.
Right, Strassen matrix multiplication algorithm. And that reduces the multiplication algorithm from cubic to the power to what is that? 2.81 something, right? Okay, so you may refer all this thing, this Karatsuba algorithm and also this one in this very famous book, Dawn of Art of Computer Programming, Volume 2, 7 Numerical Algorithms. And so it is interesting to see this multiplication problem in details, because in hardware we talk about array multiplication or the repeated shift and addition multiplication, but fundamentally this problem can be done in less than quadratic time. Although apparently it means that you have to compute n square partial product anyway, right? So apparently it means that n square is the lower bound, but it's not so. This is the power of divide and conquer and the power of reducing this. I mean, the power of using the simple algebraic manipulation that reduces the complexity of the recurrence, right? So it's very interesting algorithm not only in the history of computer hardware, but also in the history of algorithms. Well, so let me stop here today. Next time we'll discuss Booth's multiplication algorithm, and that will finish our discussion on multiplication. Well, so just to note that the multiplication is a process which is not only interesting, not only of concern to hardware engineers, but also this process has been investigated by mathematicians and computer scientists for many years in order to reduce the complexity of multiplication and expedite the process. Well, any question?